Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. I've mentioned here on the podcast a couple of times that I'm keenly interested in industrial applications of machine learning and AI. I've come a long way in my research in this area, and I'm very close to publishing a special report on the topic. If you're interested in learning more about this work when it's completed, I've put up a form at twimlai.com/industrialai. Fill out that form and I'll let you know when the report is available. In conjunction with this work, we've got something really special to debut here on the podcast. For the next several weeks, I'll be interviewing some very interesting guests working on topics connected to industrial AI. We'll be discussing different application areas like manufacturing, warehouse automation and logistics, and practice areas like robotics, reinforcement learning, and simulation. We've been planning this for quite some time, and we're very excited for you to hear what we've cooked up. Of course, as always, we love your comments, feedback, and suggestions, which you can leave on the series page at twimlai.com/industrialai. Our first guest in the Industrial AI series is Ilia Baranov, Engineering Manager at Clearpath Robotics. Ilia is responsible for setting the engineering direction for all of Clearpath's research platforms. He likes to describe his role at the company as both enabling and preventing the robot revolution. He's a longtime contributor to the open source robotics community and ROS, an open source robotic operating system. In our conversation, we cover a lot of ground, including what it really means to field autonomous robots, the use of autonomous robots in research and industrial environments, the different approaches and challenges to achieving autonomy, and much more. This was a really fun interview, and I'm excited to share it with you. Before we get started, I'd like to give a huge thank you to the team over at Bonsai. Bonsai, who is supporting this podcast series, as well as my forthcoming report, has been a big supporter of my research in this area. Bonsai offers an AI platform that empowers enterprises to build and deploy intelligent systems. I've been following them since their initial launch just over a year ago when I met the founders at a conference, and I've been very impressed with both the team and technology. If you're trying to build AI-powered applications focused on optimizing and controlling the systems in your enterprise, you should take a look at what they're up to. They've got a really unique approach to building AI models that lets you use high-level code to model the real-world concepts in your application, automatically generate, train, and evaluate low-level models for your projects using technologies like deep learning and reinforcement learning, and easily integrate the models into your applications and systems using APIs. You can check them out at bons.ai and definitely tell them that you appreciate their support of the podcast. And now, on to the show. All right, everyone, I am on the line with Ilia Baranov, who is an engineering manager with Clearpath Robotics. And I'm excited to have Ilia on to talk about the intersection between robotics and machine learning and AI. How are you doing?
Oh, I'm doing great today. Thank you.
Awesome. Why don't we start with a little bit of your background? Can you tell us a little bit about, how you got to Clearpath?
For sure. So I've always really liked robotics ever since a young age. I probably started out with Lego, as I'm sure most of us start out this way. and I really wanted to work at or go to school at University of Waterloo due to their co-op program. So when I joined them in the first year, I joined the robotics team. And at the time, we had a pretty broad robotics team where the first years would do sort of small competitions with sumo robots and line following. And then the upper years would usually work towards their capstone project or final year design project.
Okay.
And so I really liked this one group that was doing a capstone project that was doing autonomous mine sweeping. And so I asked to help them out instead of doing the first year stuff, because by that point I had kind of gotten beyond the kind of line following stuff.
Okay.
And so I ended up helping them out with their GPS solution to position their robot. And that team turned into Clearpath, essentially.
Oh, wow. Okay.
Yeah, so it's quite interesting. There's a lot of learning to do, especially in the first year. One of the funny things that ended up happening is a little bit of the code and firmware that I wrote and Ryan Garpy wrote um, made our robot kind of go in circles whenever it'd get to its actual waypoint that it was designated to go to. Because we didn't really have any good kind of tolerance on our GPS goal. So it'd get
Oh,
there and
nice.
then GPS would drift a little bit and so it'd chase it and GPS would drift a little more and it would chase it back. And so
Oh, wow.
so yeah, that's the kind of funny things that happens when you're trying to do this stuff in university.
Uh-huh. Well, I think it would help folks understand a little bit more of the context of what we're talking about if we go into a little bit of Clearpath. What is the company focused on?
Yeah, for sure. So out of those kind of roots, the four founders decided that they would try to have a go at it and create robotics for research. But they actually started on the idea of, can we take this mind-sweeping robot idea and actually apply it to the real world? And they were
Okay.
fairly surprised to find out that, large defense industries didn't want to buy from four guys in a garage. So, so they had to kind of switch their idea, and so they went with what they knew. They knew that they understood the kind of university level research application of robotics. They had talked to a lot of professors, and so they decided to create platforms.
Hmm.
So Clearpath really got started creating robotics platforms for research.
Okay.
So the idea being that if you're a researcher and you're trying to do some work, outdoors or indoors, any kind of development for robotics for positioning or movement or interaction, instead of spending the term, you and your grad student creating this robot, you would purchase one from us already integrated with the sensors that you wanted to use.
Hmm. Okay. Got it.
Yeah, so this kind of platformed approach to research robots, and especially our kind of niche that we found was the outdoor rugged market, because there had been a lot of indoor ones, like the Pioneer from, sorry, I'm forgetting their name right now. But yeah, there have been a few kind of indoor robots before, but nobody had really done an outdoor robot platform at the time.
Okay. When I look on the Clearpath site, it's not just, one or a couple of different types of robots. There are a bunch of different platforms, both kind of these ruggedized outdoor ones, as well as some indoor ones. There's UAVs. There are ones for the, it's called USV.
Hmm.
Sea vehicle. And there's even a video of one towing a plane. Is that a real application of one of these robots?
Not quite. Actually, it's funny you should mention that. That was actually a fun shoot we did for the Discovery Channel, where we tried to
Okay.
find the limits of the towing capability of our Grizzly platform.
Okay.
And by the time we had towed a fully fueled jet pretty much up a little incline, you can't really see it in the video, but the actual tarmac there is sloped.
Okay.
We couldn't really figure out what was the next big thing we could tow, so we
Oh,
kind of stopped
nice.
there.
Nice. Nice. Well,
uh,
I mean, it looks awesome. It's very impressive.
yeah, yeah, it's a lot of fun, definitely. Yeah, so the Grizzly and the more modern version, the Warthog, is meant for outdoor heavy work. So agriculture and mining is really two of the places where we've seen a lot of interest there.
Okay.
So it's funny. You could find these trivial sounding applications for these things that have a real need. For example, we worked with a vineyard where they had a problem where they'd have birds come and eat the grapes constantly.
Mm.
And so there's two real solutions to this. One is you put up bird netting, which is crazy expensive because you have to cover vast fields with this fairly expensive mesh.
You're not about to tell us about a autonomous scarecrow, are you?
Pretty much, pretty much. Yeah. So the other solution they went with is they made bird bangers. So they're basically this
Okay.
big propane air cannon that goes off every once in a while, makes a loud sound, and scares them off.
Oh, wow.
Yeah, but the crows in particular got clever, and they figured out that the bird banger was always in one place and didn't really scare them anymore.
Hmm.
And whenever people would move around the bird banger, the crows would notice that people were carrying it around, and they just move away from that area, but still eat the grapes elsewhere.
Oh, wow.
And so what we ended up doing is mounting one of these bird bangers on the Grizzly and have it autonomously drive up and down the rows very
Uh-huh.
quietly, and then let it off, and then go to the next spot quietly and let it off. And because
Huh.
it's electric and it's so slow, or it could be made to go slowly, it worked. It scared them off.
Oh, that's awesome.
So, it sounds like a completely ridiculous use case, but it actually, it was worth the time. It was worth the money. The complexity was low enough that we could actually assemble this application pretty much from building blocks.
Hmm. And now, was this a research application, or is this does the company also do commercial/industrial solutions?
Yeah, absolutely. So that one was research, but in the last few
Okay.
years, what we've done is we've created this new division inside of Clearpath called Automotors. And
Hmm.
so what Automotors does is we create these indoor platforms, the Auto 1500 and the Auto 100, to move around payload indoors. So in a factory or warehouse setting is kind of our target market right now.
Okay.
So we took a big chunk of our team. We grew from roughly 20 people when I joined, and now we're about 187. And most
Mm.
of that growth has come from the automotor side.
Okay. And now I'll mention this because it was initially confusing to me. The Clearpath Auto Motors has nothing to do with the autonomous truck company that Uber bought,
No, it does
but they
not.
were spelled the same.
Yeah, yeah. It kind of sort of happened that we filed that automotor or auto trademark and branding a little
Uh-huh.
bit before that. And yes, the two companies are totally unrelated. Just a total coincidence.
And the Auto Motors platform is somewhat reminiscent of the Kiva style of autonomous warehouse materials handling robots. Do the Kiva's kind of deployed as this entire system. Are you guys focusing just on the robots, or are you also developing this entire warehouse automation system to go with them?
Absolutely, we're doing the entire system all at once. And one
Okay.
thing I'd like to kind of point out is that Kiva, in my mind, is a little bit more of the old school style of robots, wherein every single robot individually is actually fairly dumb.
Mm-hmm.
They'll follow QR codes on the floor, and they get commands from the control system to go from point A to point B in a straight line, and that's it.
Right.
Right. And when they do their pickup operation, it's essentially a blind pickup operation. And so the entire system is only applicable when you have a kind of lights out warehouse where there's no humans beyond a certain point.
Mm-hmm.
Whereas the systems that we make are actually intended to work with humans.
Okay.
And so they're intended to take the same walkways that you'd see forklifts drive down, the same walkways that you'd see people walk around. So we think our system is a lot more flexible because you don't have to structure the entire warehouse around the robots.
Mm-hmm.
In fact, ideally, really nothing changes because it's infrastructure free.
Okay.
You could have any factory could drop in a few autos and they could get to work on day one pretty much.
Oh, that's awesome. That's a great distinction to make. And it's also a good segue into one of the big questions that I've had, or really a distinction that I think is worth exploring at least is, I think in the robotics field, we throw around the term autonomous quite a bit, or I've seen it thrown around quite a bit. And I'm wondering, I'd like to explore what exactly that means, right? I think, just given the example you just provided in terms of the way the design principles of Otto relative to Kiva, Kiva will call their robots autonomous as well, but they're, being controlled and directed by some central machine. So autonomous doesn't necessarily imply intelligent, let's say.
Yes,
How do
absolutely.
you guys think of what autonomous means, and is there any standardization around that term in the robotics industry? Like there are levels of standardization of what it means to be self-driving or autonomous in the automobile industry.
They're starting to be, and they're mostly focused around the concept of safety.
Okay.
So, what level of safety is it to work with these robots in human areas?
Okay.
And so, and this goes back really to the older, still current welding style robots for car plants, for example,
Mm-hmm.
where the arm will come down and weld a specific point completely blindly.
Right.
It has no concept of what it's doing realistically. It has no concept of what's in the way. And
And
so
if
it will
someone's in its
gladly,
way,
yeah, it will gladly smash right through somebody,
yeah.
right? And so that I would call now I'm unsure if there is a kind of a growing term, but around here what we say is that systems like that are automated,
Mm-hmm.
but they're not necessarily autonomous.
Okay.
So that the system is doing a thing automatically, it is repeating the same motion, but it is not actually planning its own path. It's not making its own decisions.
Mm-hmm.
And so that's the case here as well. And we've had, there have been mobile robots inside of factories for quite a while. I mean, Toyota has been making them probably since the 80s.
Sure.
And Yeah, and these systems will follow magnetic tape on the floor or buried markers, and they'll go from station to station. They'll pick up a load, they'll go somewhere else and drop it off. And again, I consider that system automated, but it's not really autonomous. It only follows a very specific set of instructions, and it
Hmm.
can't deviate, it can't replan, and if anybody trips its safety laser, it will just stop. It has no other option.
So then, going back to our mobile scarecrow, if you will, when you say that it's autonomously navigating the vineyard, to what degree is it actually doing that autonomously?
Yeah, absolutely. Well, I mean that specific one was kind of more of a test case here in Niagara region. So that one was actually just using GPS waypoints, going from point to
Okay.
point to point, and if it saw something in front of it using a stereo cam rig, it would just stop.
Okay.
So that was one of those cases where it's kind of automated but not autonomous.
Okay.
However, the in the auto cases, what they're doing is they actually use laser scanners to build up a map of the environment and find their own path through the environment.
Okay.
And so they're actively, each unit is making its own decisions. Even though we have this overarching dispatching system that will command each units to do certain tasks,
Hmm.
the actual execution of that task is usually up to the robot itself.
Okay. Interesting. And to what degree at Otto are you getting into, notions of the robots collaborating with one another or with humans?
Yeah, absolutely. So with one another, the one kind of interesting story I can tell is there's a client we have where we're working towards replacing the standard assembly line essentially. So you can imagine vehicles or machines going by on an assembly line, and if you have a different range of products, you could have three different assembly lines for a simple, a medium, and a very complex product, for example. So instead of that, what we're doing is the robot actually carries the product, and then there's only one assembly line. And so, as the large Auto 1500 is carrying the product, smaller robots are driving up and delivering. Here's a simple part for the cheap model. Here's a much more complex part for the expensive model. And oh, by the way, the more complex model needs more time for assembly. And so the robot will drive slower and it'll have bigger buffers between it and the next Auto 1500.
Hmm.
So if you can imagine it, it's this totally mobile assembly line using robots as the actual carriers.
Right. Oh, that's interesting.
Yeah, absolutely. And so that's a case where not only are robots collaborating with each other because you have smaller deliveries to larger deliveries and this kind of dynamic spacing, but you also have humans collaborating directly with the robots where they know that their parts are arriving just in time for them to use. And yeah, and you can imagine there's hundreds of different ways that this is more optimal than an assembly line.
Hmm.
If something is too slow or something gets broken or something's not quite right, that can be pulled out of the assembly line without the rest of the assembly line even noticing. And since the dispatcher system is keeping track, it will automatically adjust the distance between robots.
In general, when you're deploying a system like this, what's the kind of level of abstraction, if you will, that the customer needs to deal with?
Yeah, that's a great question. So we have this entire mapping system, and
Hmm.
if you could kind of imagine, let's take a case of a small manufacturer. So they want to use the Auto 100 to move parts around a facility.
Right.
So on day one, an Auto 100 arrives at their facility and they drive it around. So this first step, they're physically driving it with a little joystick. The idea being that humans are, especially people who work at the facility, much better know what is a dangerous area and what's a safe area than a machine could.
Hmm.
So for the initial step, we really don't want them driving autonomously. We want somebody to kind of shepherd them around.
Hmm.
As it does that first pass, it builds up this map of the environment that is then uploaded to the control system or the dispatcher. And after that, all the robots now know this map, and the user, from an abstraction perspective, they get this two-dimensional floor plan that they can then draw on with just a mouse click. This is cell one, this is cell two, don't go here. This is a one-way zone, this is a slow speed zone, so on and so on.
Hmm.
And so they're essentially painting in the map in what style that they want the robots to work in.
Okay.
And lastly, the robots are also able to detect what is a charging station, what is a docking station if they need higher precision. And those are features automatically added to the map. So at the end of this, first day, the user has a map of their plant. They know where all the cells are, where the charging stations are, and where all the robots are positioned. After that, they can either do individual commands and tasks or fleet-wide commands. So they can tell a robot, I need you to go from here to here right now. And that's a kind of a one-time command. Or you could set up a chain saying, I need robots from this dock to this dock every 30 seconds.
Hmm.
and then it takes off.
Okay. And then a next level would be integrating that in with some type of plant management system that is, based on kind of flow of, machines and materials, or integrating it into a CNC or something like that where does that, integrating into the broader production pipeline, where does that fit in?
Yeah, so that's not something we've started out quite yet. That's definitely on our roadmap.
Okay.
However, we have a lot of integration partners that have started doing that. So we have seen quite a few different full robotic arms and dual manipulator systems mounted on top of auto units.
Oh, wow. Okay.
And actually, at this year's ICRA 2017, we're going to have a UR5 arm on top of a Ridgeback, which is our research robot. But the research robots are also now deploying this autonomy research kit for use by researchers. And one of the
Mm-hmm.
demonstrations we'll have there is trivially scripting the arm to pick up an object, drive somewhere, and put it down in about 5-10 lines of code.
Okay. Oh, wow. One of the things that you mentioned that has come up in my research as being really important and in a lot of ways distinct from the treatment of AI and robotics in kind of the academic literature is this idea of, learning from the subject matter expertise that is inherent in the customer environment or the ultimate deployment environment of the robot. So, for example, you talked about, hey, let's let humans drive the robot around. So, we don't have to let the robot, bang around the warehouse for a week to try to figure out, what's what.
Yeah.
And then, letting humans then come in and, put markings on the map to identify, areas that, robots shouldn't go or should go, or directions, things like that. I'm curious your perspective on that, that notion generally of, capturing, human expertise in the programming of the robot with AI, and, any challenges that it represents, other areas that you might see it come up, things like that.
Yeah, for sure. So one of the early problems we had was when we were looking into getting these robots into factories, we had two different responses. One of them was, this is fantastic. The robot can go anywhere. I don't have to do any planning. It will just figure everything out,
Right.
which isn't quite right, because really to get to that kind of level of information, you're talking about a general purpose AI, which we're
Uh-huh.
not we're not close to.
Right.
And then the other end of the spectrum, which we also got, was, well, how can I depend on this thing if it's not exactly following this path that I laid on the floor for it?
Mm-hmm.
And so some of our early efforts involved putting virtual tape into the map.
Okay.
So behaviors to tell the robot that I need you to follow this exact path and don't deviate from it. If anything gets in your way, stop. Otherwise, keep going.
Mm-hmm.
And that kind of behavior really comes from the learning that a lot of the times in the academic community, getting the thing to work and work well and not crash into things is quite an achievement. And it's quite difficult. That's what we spend a lot of time on.
Mm-hmm.
But especially when you're talking about industrial use cases, the customer is looking at it as equipment. They're not really looking at it as this self-driving vehicle. And
Mm.
so they don't care that it's, doing these magic, right? Creating maps and navigating. They care about what is the takt time, how efficient is it, and what is its
Mm-hmm.
downtime.
Mm-hmm.
And a lot of the time, you will find that through these people working there for years and years, they know what the most efficient route is. They know that even though this route is longer in terms of footpath or absolute distance, it will take a shorter time because it tends to be less congested, for example.
Mm-hmm.
So adding in that human layer knowledge of, here's an area that is more clear usually, is kind of an interesting trick that we've had to fuse the best of human knowledge of the environment with this kind of superhuman level of planning and optimization that computers can do.
Great. Great. Can you talk a little bit about all of the various ways, maybe catalog the various ways that you guys use machine learning and AI with the auto systems?
Yeah. So some of the things we're really looking into, one of them, it's sort of on the border of machine learning, but one of the main kind of problems of creating these systems is getting an accurate map. And
Okay.
so there's a standard way to use laser data and turn it into a map just by basically it's called GraphSlam. And
Okay.
that method works well on its own, but it does have inherent problems of kind of distortions and things like that. So you do have to apply a little bit of intelligence to the way that you're creating these maps, and that
Mm-hmm.
that on a factory floor, for example, it would be very unlikely for the outer wall to curve,
Right. Right.
right? So that just doesn't look right to a human, and so it shouldn't look right to our algorithms either in that way.
Mm. So you're doing things like maybe classifying points and curve fitting and that kind of thing to try to generate the ultimate map.
Generate much better maps, yeah. And
Okay.
the kind of the step further than that is after we have a decent map, we can also think about, can we classify obstacles in that space? So just using laser data or perhaps camera data or ultrasonic data, can we classify that I'm fairly confident this is a forklift? If this is a forklift, that means that it has these large tines. If I can't see the tines, then either they're out of my laser scanning range or something else is going wrong. So I'm going to give this an extra wide berth because I can't tell where the hazard is.
Mm. Mm-hmm.
Or otherwise, oh, I do see the tines. I know exactly where it is. So I'm going to shrink my approach distance and I can be more efficient in my pathing.
Okay.
So obstacle recognition and being able to predict what an obstacle is going to do in terms of movement or speed or direction is definitely something that makes planning more efficient.
Mm-hmm. And then how about in terms of the robot, the navigation? I mean, we've talked about a little bit of the pathing. Is all of the pathing more or less deterministic? Outside of the fact that it has to detect objects and react to them. Is the general path it takes more or less set, or will one of these robots ever deviate if it knows of an alternate path and finds some obstacle that isn't moving or not moving quickly enough?
Yeah, absolutely. So it's making a constant projection of how long it's going to take to arrive to its end goal,
Okay.
and it's updating the system. So the system knows this robot needs a 30-second tack time from point A to point B, and it's only going to make it
Mm-hmm.
in 32 seconds. So something's not quite right. So this path is
Mm-hmm.
either not possible to do in this time, or there's more deterrents or obstacles in the way than there should be at this time.
Mm-hmm.
And so the robot's constantly making this projection of what is the fastest way to get there? What is the most efficient way to get there? And if it's on a path and it sees obstacles, or even if other robots in the space have detected those obstacles and uploaded them to the supervising system,
Mm-hmm.
then that robot will know, okay, this is likely a less ideal path, so I'm going to take this alternative path.
Hmm. Can you talk a little bit about maybe the difference between machine learning and AI that is running on the robots versus running on the supervising system? What functions maybe sit where?
Yeah, I can talk a little bit about that. Ideally speaking, we don't want to have our individual robots constantly trying to adjust all the time or constantly trying to learn all the time.
Mm-hmm.
So, because this runs into one of the fundamental problems you have, especially applying AI in industry, is that you have to be provably safe,
Right.
especially with these machines being very large and fast. You have to be sure that even though there's a hardware safety system on board, triggering a hardware emergency stop is not a desirable effect,
Mm-hmm.
because
Right.
you've just, at the very best case, you've messed up your tack time.
Right.
You've messed up your delivery window.
Mm-hmm.
But in the worst case, you can't stop fast enough and you actually hit something.
Yeah.
So we need to ensure that the robots on the robot level have as predictable behavior as possible.
Mm-hmm.
And this even goes up to the level of, if you'll notice, the Auto 1500s and the 100s have a LED strip around the edge.
Mm-hmm.
And so what we do is, because especially the Auto 1500, it's fundamentally doesn't really have a front and a rear. They're almost a mirror image of each other.
Okay.
And so the robot doesn't care if it's going forwards or backwards. And so that leads to a lot of confusion for people because they couldn't tell what the robot was planning to do.
Right.
And then people will naturally, if you can imagine, you see this machine behaving in an unpredictable way, you'll naturally start to stop and be wary and kind of clog up the route.
Right. Right.
So having people comfortably know where the robot's planning to go means they'll naturally clear out of that space. And then it's kind of a reinforcement effect in that the robot will move better.
Mm-hmm.
And so that LED strip, what it actually does is it actually puts headlights at the front and taillights at the back like a car.
Okay.
And it will actually blink yellow blinking turning signals when it's turning in one direction or the other. And
Okay.
people really respond naturally to that because we have this kind of built-in language for roads.
Right.
What does it look like when a car's coming to a stop? Well, the back red taillights will flare brighter.
Right.
What does it look like when it's trying to pass? Well, it might blink the white front lights telling you, go ahead, you go first.
Mm-hmm.
And so all these kind of behaviors really make it much more predictable in its movement. And as a side effect, they make it more safe.
What else goes into, I mean, so you've talked about safety systems, but do customers, you mentioned provably safe. What goes into the proving of the safety, and to what degree do you have to do that? Are there specific regulatory requirements that you run into that have standards for proving safety, and what are those and how do you address them?
Yeah, absolutely. So there's one of the fields where we're seeing here is that a lot of the standards in industry for so-called collaborative robots are really designed around collaborative arms.
Mm-hmm.
So Universal Robot or the Baxter from Rethink,
Right.
these are robots that are intended to work with humans. And so they're very, very clearly defined on maximum inertias, pinch points, and things like that. But actually proving that a system that is mobile on the ground, that's a much more tricky story.
Okay.
So there's a large set. I think we currently follow 12 or 13 different standards for safe systems working with people.
Okay.
And so from the very basic level, things like the emergency stop system has to be dual redundant.
Mm-hmm.
So at any given time, if any one system fails, the system can still stop safely.
Mm-hmm.
Other things going all the way up to our planner on the robot itself should never plan into a space that it can become unsafe. So even in the worst case scenario, some horrible bug freezes the entire computer, the robot should still be able to stop itself safely.
Mm-hmm.
Right? And so there's multiple levels here. You have the highest level, which is the supervisory system commanding robots and kind of hinting them a most reasonably safe path.
Mm-hmm.
Then you have the actual autonomy on board the robot, ensuring that it's going at a safe speed with a safe clearing distance in front of it and planning into a safe space. Then a lower level down, you have the microcontroller that's doing the low level command and real time control of brakes, motor encoder values,
Right.
and those kind of things. And then even outside of all that, you have this completely separate hardware safety system that's tied into the safety lasers, so that when the lasers are set to a mode that it's expecting the robot to travel at 1 meter per second,
Mm-hmm.
we know that the robot will stop at this speed in 1 meter second. So the laser, safety trip range has to be at least this far.
Okay.
And so a lot of the challenge to build this safe system was, can we prove and can we test out that the robot will actually stop at this speed under all of these conditions?
Right. Right.
And so how we did that is we actually have a motion tracking system similar to what's used in the film industry. And we put tracker dots all over our robots and we would run them at cardboard obstacles over and over again for hours from different directions, different speeds, different payloads, everything, and figure out exactly how long it takes to stop in all of these conditions.
Okay.
And one of the interesting things we found out is there's actually a slight omission in some of the safety standards, in that the safety standard assumes if you're going around an arc or curve, if you stop the motors, so you remove power from them, the robot will naturally go in a straight line.
Mm-hmm.
So you can imagine, you're swinging a weight on a string. If you let go, it should travel in a straight line.
Right.
But that's not the case, because you actually do have rotational momentum on your robot.
Mm-hmm.
So you will actually you will continue to go in a curve. Not as much of a curve as you were going, but more than you would expect.
Right.
And so these kind of things are really hard to see unless you do these thousands of hours of testing and you track it down to the millimeter. But that really shapes the way that our laser safety field sets work.
Mm-hmm. Yeah, and it seems like that doesn't even take into account the physics of whatever your payload is. If you've got a bunch of palletized things stacked up, 10 feet tall, you're going to have a kind of a dispersion radius of things all over the warehouse floor that you need to kind of keep track of if you're trying to figure out, what the dangerous radius around this robot is.
Absolutely. Yeah. And so the kind of next steps that we're really looking into is, can we use our load sensors to ensure that we never tip anything over, even if somebody puts something improperly on the top of the robot?
Mm-hmm.
Can we use camera systems to ensure that we have looking around corners that the robot can't see,
Mm-hmm.
and so to start braking ahead of time? Can we project light ahead of the robot so that people can know that the robot's coming around the corner?
Mm-hmm.
Those kind of systems. Yeah, there's definitely there's lots and lots of different directions to go, but at the most fundamental level, it's ensuring that your systems are dual redundant and you have a completely hardware based safety stop system.
It sounds like in a lot of ways there's a convergence between industrial robotics and consumer autonomous vehicles, and the technologies that are perhaps accelerating due to the interest in self-driving cars are going to kind of find their way into the industrial realm. Are you guys seeing that?
Yeah, absolutely. And undoubtedly, the consumer autonomous vehicle market is a very large market.
Mm-hmm.
But in my opinion, it's a much more difficult market to capture.
Right.
The nice thing about the inside of a factory is it never rains. So
Hopefully
you're
we
never
keep
gonna
the
have,
fire sprinklers off, right?
yeah, exactly. So you're never gonna have rain, you're never gonna have fog, you're
Uh-huh.
never gonna have ice. And so these are all things that we don't have to worry about. And so we have much more predictable systems. And so a lot of the times it's actually kind of nice that um, the autonomous vehicle market is thinking about all these problems to make their lasers and cameras more robust against these effects
Mm-hmm.
that we don't even have to worry about. So we get this additional robustness essentially for free.
Mm-hmm. To what degree do you guys use reinforcement learning? That's technology that has come up quite a bit in my research into these systems. Is that something that you guys are looking at or using?
We're definitely looking at it, especially as I mentioned with the idea of, can we classify obstacles that we see in our space?
Mm-hmm.
But that isn't yet released into our actual industrial offerings at the moment.
Okay. And so over time you're adding more capability in terms of like computer vision and things like that generally to be able to detect and differentiate between various obstacles, so that is that primarily for the safety use case, or are there other things that you envision the robots doing with the ability to make those kinds of distinctions?
Yeah, so the real three things are safety, efficiency, and accuracy.
Okay.
So with safety, having a stereoscopic camera system, such as on the Auto 100, allows you to see obstacles outside of the field of range of the LiDAR.
Okay.
So especially the Auto 100, we expect it to be used more in cluttered environments and smaller environments. So it really needs to see that there's a desk that's up above where the LiDAR can see to ensure that it
Mm-hmm.
doesn't crash into it.
Right. Right.
The second idea in terms of efficiency is, if we can classify obstacles, we can figure out what their behavior and movement is. And so naturally as a person, if you're walking down the street and you see somebody walking towards you, I mean, and sometimes humans will make this mistake, but you'll go to the left, they'll go to the left, you'll go to the right, they'll go to the right. You could do that little dance.
Right. Right.
So the idea here is, can we kind of heuristically figure out a way to ensure that robots don't do that kind of behavior, that they actually have almost a personality. They'll tend to stick to the wall when they see a person.
Okay.
They'll very visibly get out of your way.
Okay.
Or vice versa. They're carrying something very heavy, and very quickly they'll sound an alarm, even though you're not in the range, you're not in the way yet. They'll warn
Right.
you ahead of time because they know you might get in the way.
Right. Right.
And so those kind of things. So that would be kind of the efficiency state. Well, I mean, and safety again as well, but also ensuring that the robot doesn't have to veer out of the way,
Yeah.
or it can plan ahead of time.
Yeah.
And lastly, in terms of actual localization, camera gives you several orders of magnitude more rich data than just a laser. And so you can start positioning yourself based on paint or markings or, you name it, light fixtures.
Mm-hmm.
And so that gives you this added level of robustness and accuracy in terms of positioning yourself in three-dimensional space.
Okay.
And all those things actually require machine learning quite to a large extent.
Mm-hmm.
You have to understand that even if this obstacle doesn't look like it's in the way, if you recognize it as a table, you can make certain assumptions like, okay, well, tables usually touch the floor. And so even if I can't see the legs on the other side, I know there's something on the other side. And if I know roughly the dimensions, I know roughly how big I have to avoid this obstacle by, even if I can't see the other end of it.
Right, right. Yeah, one of the challenges that I think you're trying to overcome with the computer vision applications is the lidar is generally only giving you a two-dimensional kind of lay of the land, right? And it's typically they're mounted pretty low, so like anything that's around knee level it sees, and anything below or above that it's kind of oblivious to. Is that the way yours work as well?
Yep, that's close. I mean, we try to mount ours right about ankle level,
Okay.
or as low as we possibly can,
Okay.
because you really want to see people's ankles or feet ideally. That way you know exactly what their contact point to the floor is.
Okay.
But yeah, as I mentioned earlier, kind of one of our early issues we had a lot was forklifts. So a forklift driver who didn't put his tines down,
Yeah.
so the two kind of big forks at the front,
Yep.
they would be sticking up in the air right about knee level,
Okay.
which is kind of a deadly area if you think about it, because it's just out of range of the LiDAR.
Yeah. Yeah.
And so that was quite tricky. And you're really playing this balancing game. You theoretically you want to be right at ground level. But the problem with that is A, you can't really mount a laser that low because you'll just start to scrape it on the floor.
Mm-hmm.
And the other problem is that floors aren't actually that flat.
Right.
And
Right.
so you do actually, there's another aspect there of kind of human guided machine learning where you want the robots to understand that this is not an obstacle, nor is it a hill. It's just the floor is slightly uneven.
I would have thought that, the poured concrete floors would be a lot more flat and reliable than anything in my old wood floored house.
You would be amazed. It's really a factor of distance, right? Your
Right.
factory floor is so massive
Yeah,
that
true.
a 0.1 degree difference turns into, a few feet.
Yeah.
So it's quite surprising.
So tell me this, are there any particular, beyond the things we've talked about in the computer vision domain, are there any trends or research or technologies that you're tracking in the machine learning, deep learning, AI domain that kind of have you excited for the implications to robotics?
Yeah, so what we're taking a close look at is understanding maps and understanding the behavior of mapping and positioning. So can we, for example, understand that here's a factory floor, and just off the factory floor there's a lunchroom, for example.
Okay.
And as a human, you would assume that somewhere between 11 o'clock in the morning and 1 p.m. in the afternoon, the lunchroom is going to be very busy.
Mm-hmm.
So don't bother to walk through there because you know it's going to be busy. And so, can we apply that kind of concept to our understanding of maps, to the robot's understanding of maps? So, as they're driving around, they collect this data, they send it up, and then our system can understand that this area is very busy at this time. Even though I have no vision of it, I know from last week and the week before that this area is probably too busy for me to plan through. So, I'm just going to avoid it without even trying.
Mm-hmm.
So, that's definitely an area that we're looking into is understanding maps and kind of gaining a more fundamental level understanding of how space is changing throughout the day.
Okay.
And that example that I gave is kind of the most easy to understand, but there's also, especially with small factories and small kind of cell-based manufacturing,
Mm-hmm.
things change every day. This day you're making cases for a cell phone. The next day you're making, I don't know, car dashboard accessories, that kind of stuff.
Right.
So people, but also their equipment is moving around on the factory floor, and having the robot understand that this drill press that was here yesterday is now over here, but it's the same object. So when I ask you to go to the drill press, you don't go to the old location, you go to the new location.
Mm-hmm.
So again, those are things that mapping and understanding of the space is something that we're really looking into.
So you're about to head off to ICRA, which is in Singapore this year. That's the International Conference on Robotics and Automation. Is that right?
That's correct.
What are you excited to see there?
Oh, well, all of it pretty much. We've seen quite a large growth in these two kind of fields. One is mobile manipulation. So not only having these human safe arms working in their cell, but actually moving from cell to cell. And
Mm-hmm.
so one of our industrial partners, what they did is they're working on very high precision, very trackable uh, manufacturing.
Okay.
And so, they're making jet engine parts or nuclear reactor parts. And
Mm.
so every single part needs to have a history and needs to be checked every single step.
Mm.
And so
Mm-hmm.
one of our autos is carrying around a manipulator. The manipulator will come up to a station, take a block of aluminum, put it in a CNC, start it, wait for it to finish, take it out, bring it to the measuring station, measure it, label it, track it in their database. And so we'd been working on that for a little while, but now we're starting to see a lot of different companies take a crack at that same problem.
Mm.
Is can we make multi kind of flexible manipulation?
Mm-hmm.
And the other big trend we're seeing is survey robotics. So, remote inspection of pipelines and power lines and power stations and places where it's just very far to get to, and you don't really want a human there all the time,
Mm-hmm.
but you do want to have high quality data come back from it.
Mm-hmm.
And so, those are two fields that we see even large industrial partners or large industrial or just large companies in general.
Right.
For example, DJI got started in the kind of consumer space, but they're really making inroads in the can they do remote survey of data with their drones?
Mm-hmm.
So that should be pretty interesting as well.
And I'm starting to see there are a number of companies that are trying to tackle the indoor industrial drone problem or space. For example, flying around warehouses or supermarkets to, hopefully overnight, right, when no one's in there,
Yeah, yeah,
to take inventory, which is a super expensive process for companies.
yeah.
And you guys have, are you less far? I presume I should say that, given that you have, Auto Motors, which is kind of the commercialization and kind of industrial facing company focused on the, indoor materials handling platforms. Are you kind of moving in a commercial direction with the UAV and the USV, the aerial and the seaborne vehicles as well, or are those more research oriented for the foreseeable future?
So definitely the unmanned aerial vehicles tend to be a little bit more research focused for now, at least on our side.
Mm-hmm.
Simply the reason being that the main preventer from them being used for most tasks is just battery life.
Yeah.
So if you're doing aerial surveys and you're doing aerial surveys of data, that's great. 15, 20 minutes, that's all pretty much you need to collect the data you need.
Yeah.
But if you're doing something like store inventory, you need to do an hour or 2 hours.
Right.
And it's just not really feasible. On the other hand, though, the unmanned surface vehicle, our Heron, that's an interesting case because we had actually done some work there becoming a data provider to provide data for municipalities and companies about tailings ponds and um, overflow ponds and those kind of places where you need to know the depth and water quality of a small body of water.
Okay.
And so the idea would be that different companies would take this heron out to a site, do an automated survey, a GPS guided automated survey of the depth and quality of a pond, and then that data is uploaded to us, and we provide this data as a service.
Oh, super interesting.
So that's something that we're looking into as well. So that's actually quite a lot closer to a real direct commercial application where
Mm-hmm.
the user is using it just as another piece of equipment and not really worrying about it being a robot.
Oh, nice. And maybe switching gears a little bit, you are kind of active in the open source robotics community. There's a robot, ROS's robotics operating system or robot operating system that you've done quite a bit of work with. And what's the intersection with Clearpath? Do the Clearpath platforms run some version of ROS?
Yeah, yeah. So um, Ross is this idea of can we apply the Linux ideal where Linux is free and open source and you can run it on everything? Can we apply that to robots as well?
Mm-hmm.
So the idea behind Ross is it runs predominantly on top of Ubuntu, but it can run on a few other platforms. And it will talk the same language from microcontrollers all the way up to servers.
Okay.
And so that makes assembling your robot very, very easy because you can add on an arbitrary microcontroller, almost an arbitrary sensor, because most of them now have supported ROS drivers,
Okay.
and assemble your robot almost as Lego bricks, which is what we do. And so we became a very early supporter of ROS, and we continue to be one of the kind of the largest companies that provide all of our platforms are ROS compatible, all of our research platforms.
Oh, nice. And is there a standard interface between ROS and kind of higher level machine learning AI stuff, or are those kind of two separate things at this point?
At this point, they're a little bit separate, but they're starting to get there. So one example is everybody should be familiar with the OpenCV framework for image processing.
Mm-hmm.
And OpenCV actually came out of Willow Garage, which also started ROS.
Okay.
So at the same time, Willow Garage created the kind of open source robotics movement and a lot of these early fundamental libraries for image processing, a little bit of the machine learning work, and those kind of tasks.
Interesting. Yeah, and I guess this is also an aside, but I got in on a Kickstarter for this little miniature LiDAR system called Scans. Have you ever come across that?
I believe so, yeah.
Yeah, I haven't done anything with it, which is the case with most of my electronic Kickstarter projects. But it looks like it's pretty cool that you can make all of the components in this ecosystem, from the the platforms to the UAVs to the sensors, including now LiDAR. They've just become so affordable and miniaturized. It's become very accessible, which I think contributes to people being able to do lots of things and play with different ideas, including kind of the ML and AI angle.
Yeah, absolutely. The cost of LiDARs is coming down quite significantly, and but more than that, really, the real enabler in my mind is the rapid growth of processing power for images.
Mm-hmm.
So not only the libraries are designed to run on CPUs, but also GPU-based processing of images.
Mm-hmm.
Because as nice as LiDARs are, and we use them almost everywhere, fundamentally, we build the world around humans, and humans mostly use vision for their navigation.
Mm-hmm.
And so almost everything we've structured around this idea of you have a roughly human-sized object that can see roughly human distances, and that's how we get around.
Mm-hmm.
So fundamentally, I believe that in the long run, in the next 50 to 100 years, most of our systems will start to use cameras as their predominant source. And that's beneficial even today because a relatively decent camera is maybe $20.
Yeah.
And it's more than good enough to do cutting edge research.
Mm-hmm.
And, you can start with 2 cameras that are the same model. You put them on a ruler so they're a measured distance apart. You calibrate out their small imperfections. And then you attach it to a consumer grade laptop and you have a cutting edge stereoscopic vision platform that you can start doing research on.
That's awesome. Any particular, for folks that are interested in the hobbyist angle here, any particular links or pointers or places that you find are helpful for folks getting started?
Yeah, well, I mean, I'll kind of suggest that people visit the Clearpath Robotics ROS 101 series of tutorials, where we can help people get started on ROS. We have a little virtual machine, so you don't have to install Ubuntu on your home computer. You can kind of just run it virtually, and all of our robots are simulated there along with sensors. So you could actually simulate, for example, a Husky with a stereo cam rig, with a LiDAR, with an IMU, and move around a virtual map and start doing mapping, navigation, path planning, all of that for free on any laptop.
Oh, that's amazing. I'm definitely going to have to do that. Well, you brought up simulation. That's a topic that I want to dig into also, but I fear we are bumping up against a time constraint here. So I'm going to save that for another conversation. But thank you so much for taking the time to speak with me about your work. It is really fascinating stuff that kind of speaks to the kid geek playing with Legos and trying to make stuff automated. I really appreciate you taking the time out.
Absolutely. Thank you very much.
All right. Thanks, Ilia.
Bye now. Bye-bye.
All right, everyone. That's our show for today. Thanks so much for listening and for your continued support, comments, and feedback. We're excited to hear what you think about this show and the Industrial AI series we've just kicked off. I'd also like to thank our sponsor, Bonsai, once again. Be sure to check out what they're up to at bons.ai. Speaking of Bonsai, they'll also be at the O'Reilly AI Conference in New York City later this month. If you'd like to attend, you can save 20% on registration by using our special code PCTWIML, PCTWIML. We'll include the code and a link to the registration page in the show notes. I'd love to meet up with listeners at the conference. In fact, I'm planning a community meetup during the event, and I'll share details as soon as they've been ironed out. As usual, the notes for this episode can be found at twimlai.com/talk/27. For information on Industrial AI, my report on the topic, or the Industrial AI podcast series, visit twimlai.com/industrialai. As always, remember to post your favorite quote or takeaway from this episode, and we'll send you a laptop sticker. You can post them as comments to the show notes page, via Twitter. You are following us at @twimlai, aren't you? Or via our Facebook page. Thanks again for listening, and catch you next time.